Venus is the same size as Earth, same mass, almost the same distance from the Sun, but its surface temperature is 470 degrees Celsius, hot enough to melt lead. Something turned Earth's twin into hell. The question isn't whether it happened, the question is when. This is an investigation into the most violent planetary event in our solar system, and why the standard explanation doesn't survive the math. Let's start with what we know. Venus is the second planet from the Sun. It's 108 million kilometers away compared to Earth's 150 million. It's our closest neighbor, 3 times closer than Mars, and in almost every measurable way, it is Earth's identical twin. The difference in radius between Earth and Venus is just 350 kilometers. That's nothing. Venus has almost the same gravity, the same rocky composition. If you could stand on its surface, your weight would feel virtually identical to standing on Earth. But here's where the twin story breaks apart. Venus has an atmosphere 90 times denser than Earth's. The surface temperature exceeds 470 degrees Celsius, hot enough to melt lead, and 96% of that atmosphere is carbon dioxide, but not in any form you've ever seen. Under 93 atmospheres of pressure and extreme heat, carbon dioxide enters a state called supercritical fluid. It's not a gas, it's not a liquid. It behaves as both simultaneously. Its density reaches 10 to 80% that of water. Venus doesn't have an atmosphere at its surface. It has an ocean of semi-liquid carbon dioxide. Let that land for a second. You could theoretically swim through the lower atmosphere of Venus, not breathe but float. The surface of our twin planet is submerged under a crushing ocean of carbon dioxide so dense it behaves like warm syrup. So what caused this? The standard explanation is a runaway greenhouse effect. Venus is closer to the Sun, so it got hotter. More CO2 entered the atmosphere, which trapped more heat, and the cycle spiraled out of control. Sounds reasonable, but planetary scientists have been quietly poking holes in this for decades. In 2019, NASA's GISS, the Goddard Institute for Space Studies, published a model suggesting Venus could have maintained liquid water oceans for up to 3 billion years, even at its current distance from the Sun. A physics simulation was run that accounts for solar absorption, radiation, albedo, surface heat capacity, CO2 levels, water content, atmospheric mass, and the greenhouse effect itself. They placed a copy of Earth at Venus's orbital distance and ran the model forward. After 20 simulated years, the equator reached about 78 to 80 degrees Celsius. The poles settled at around 32 degrees, hot, but habitable. They then accounted for water evaporation, increasing atmospheric density tenfold, and raised the albedo because a thicker atmosphere reflects more sunlight. The result? Temperature actually dropped. Poles at 23 degrees. They zeroed the axial tilt and raised albedo further. Poles reached -17. The planet was still livable. Read that again. Even at Venus's distance from the Sun, with a denser atmosphere and stronger greenhouse effect, Earth stays habitable. The poles freeze. Life persists. So if the greenhouse effect alone can't turn Venus into hell, what did? Planetary scientists acknowledge this gap. And the leading alternative within mainstream science is volcanism, massive, planet-wide volcanic eruption on a scale never seen on Earth. There's just one problem. There are more confirmed active volcanoes on Venus. Japan's Akatsuki spacecraft, the only probe currently orbiting Venus, was sent specifically to find volcanic activity. ESA's Venus Express spent 8 years in orbit scanning for thermal signatures. Neither found definitive proof of eruption. Venus has volcanic structures, but they appear dormant. Consider Venus's largest volcano, Mat Mons. It's hundreds of kilometers across, but its slope is barely 1 degree. NASA's Magellan radar images stretch it vertically by 22 times to make it look dramatic, and this is openly documented in the image metadata. In reality, it's flatter than a pancake, and the lava rivers flowing from it extend over 400 kilometers. Here's why that's remarkable. Lava on Earth loses fluidity and solidifies within a few kilometers. To flow 400 kilometers on a 1-degree slope would require temperatures above 1200 degrees, maintained the entire way. At a flow speed of about 15 kilometers per hour, that's a minimum of 26 hours without cooling a single degree. The only way that works is if everything around the lava was already just as hot. Stop and think about that. The lava didn't create the heat was already there. Something had already superheated the entire planet. And then there's the acid rain. Sulfuric acid clouds sit in Venus's upper atmosphere, and everyone calls them terrifying. But here's the detail that changes the picture. Sulfuric acid decomposes above 450 degrees. It breaks down into water and sulfur. Since the surface exceeds 460 degrees, acid rain literally evaporates before it ever reaches the ground. The sulfur dioxide in Venus's atmosphere is just 0.016%. Atmospheric models show it should have been consumed by surface reactions within a geologically short time. It should be gone, unless something is constantly replenishing it. The standard answer is volcanoes, but there are no confirmed active ones. So where is the sulfur coming from? Now here's where this investigation takes a sharp turn. Because the strangest thing about Venus isn't its heat, it's its spin. Every planet in the solar system rotates counterclockwise when viewed from above the North Pole. Mercury, Earth, Mars, Jupiter, Saturn, Neptune, all the same direction. It's a fundamental consequence of how the solar system formed from a spinning disk of gas and dust. It all goes back to the protoplanetary disk. A cloud of gas collapsed under gravity, began to spin, and flattened into a rotating disk. The outer edge of each forming planet moved faster than the inner edge, imparting spin in one direction. This is not optional, it's physics. Every planet should spin the same way. Venus spins backwards, and not just slightly. Its axial tilt is 177 degrees, almost perfectly upside down. If you stood on Venus and looked at the Sun, it would rise in the west and set in the east. The entire planet is flipped, and it's the second closest planet to the Sun, one of the last places where this should happen. Planetary scientists have proposed three main hypotheses. First, a massive impact flipped Venus over. But calculations show any impact large enough to reverse the spin would destroy the planet. Second, gravitational tidal forces from the Sun gradually slowed and reversed it, but no published model produces the full 177-degree tilt. Third, atmospheric torque. This remains deeply contested. Three theories, none fully works. So let's try a fourth and see if the physics holds up. What if it wasn't one single impact but many? A bombardment. Not one city-killer asteroid, but a swarm of massive objects pounding Venus one after another, each one adding angular momentum in the wrong direction. A simulation was run. A single 200-kilometer asteroid hit Venus head-on. Result, the axis shifted less than 0.4 degrees. They scaled up to a 2,000-kilometer object, essentially a dwarf planet. Result, the axis flipped 175 degrees, close to the 177 we need. But the planet started spinning too fast, one rotation every 4 days instead of Venus's actual 243. Then they tried 20 asteroids, each 500 kilometers across, launched sequentially. The result was remarkable. The axis shifted over 130 degrees. The planet stayed intact, and the reversal took nearly 2 months, far more realistic than an instantaneous flip. Adding just 5 or 10 more objects would push Venus past 177 degrees. And this scenario explains everything else too. 20 massive impacts would heat the entire surface to nearly 200 degrees. Everything organic would incinerate, releasing enormous volumes of carbon dioxide. The kinetic energy of the collisions would blast sulfur compounds into the upper atmosphere, where they remain to this day, unable to fall back down. One hypothesis, 4 problems solved: rotation, temperature, sulfur, and lava flows. Let's keep pulling this thread. This also resolves the sulfur puzzle. Sulfur wasn't pushed up by volcanoes through 93 atmospheres of pressure. That's physically implausible. It was blasted into the upper atmosphere by the raw kinetic energy of cosmic impacts. Once there, it forms sulfuric acid clouds that decompose before reaching the hot surface, creating a permanent sulfur cycle. Now look at the surface features. Venus is covered in circular formations that scientists call coronae, structures that look like giant splash marks. NASA's Magellan mission mapped 168 of them across the planet. If a single mega impact had melted Venus, the surface would have cooled into a smooth plane. But coronae form specifically when large objects strike an already molten surface. Compare Venus's surface to the Moon. Strip away the false color processing applied to radar returns and look at the raw grayscale data. Craters, plains of solidified lava, plateau regions, scars from impacts. The resemblance to the lunar surface is striking, except Venus has an atmosphere trapping all the heat, so it's cooling far slower. Now, speaking of what we've actually seen on Venus' surface, let's talk about the only photographs ever taken down there. The Soviet Union sent 16 spacecraft to Venus between 1961 and 1984 as part of the Venera program, the most ambitious Venus campaign ever attempted. They were the only nation to land on the surface and transmit photographs back. The images showed flat, rocky terrain under a dim orange sky. And then Venus exploration nearly stopped. From 1961 to 1984, 24 spacecraft visited Venus. In the 36 years after that, only 6 more went anywhere near Venus. NASA's Magellan mapped Venus by radar, then was deliberately deorbited in 1994. After that, over a decade of nothing. That's finally changing. NASA's 5 VERITAS and DAVINCI missions are scheduled for the early 2030s. ESA's Envision orbiter will follow. For the first time in decades, we're going back, and the data these missions return could settle this debate one way or another. But we don't have to wait for those missions, because the existing data already tells a story, if you look carefully. Let's examine the temperature data more carefully, because even that might not be what it seems. The first spacecraft to reach Venus's surface was the Soviet Venera 7 in December 1970. It landed on the night side. Venera 7 entered Venus's atmosphere at 11.2 kilometers per second and experienced 350 Gs of deceleration. For comparison, the Space Shuttle Columbia entered Earth's atmosphere, which is 90 times thinner, at a gentle angle and far lower speed, experiencing only 7 to 8 Gs, and the 2000-degree plasma from friction still tore Columbia apart. After landing, Venera 7's telemetry commutator had failed. Its exact position was calculated only from Doppler effects. It transmitted temperature data for just 20 minutes, 475 degrees at the surface. But a fair question, was that the temperature of the atmosphere or the temperature of the semi-liquid CO2 heated by the probe's own superheated hull? This isn't conspiracy. It's basic experimental design. A white-hot probe plunging into dense fluid will heat its own surroundings. That's thermodynamics. The Americans tried in 1978 with Pioneer Venus 2. They launched 4 descent probes, 2 aimed at the night side. Both night side probes failed on impact. The surviving probe landed on the day side. Reliable night side surface data has never been independently verified. And yet, the textbook claim is that the temperature is uniform everywhere. Consider this. Venus rotates so slowly that one Venetian day lasts 117 Earth days. That means the night side faces away from the sun for nearly 2 Earth months straight. On Earth, even one long winter night can drop temperatures by 80 degrees. Could Venus's night side be significantly cooler? Even on Earth, with its quick 24-hour rotation, temperatures swing from -80 to +55, a range of 135 degrees. Scaling proportionally, Venus's night side could plausibly be 200 degrees cooler than its day side. That would put night temperatures around 250 to 270 degrees, still extreme, but a completely different picture from the uniform 470 claimed in textbooks. And here's the detail that makes this more than speculation. Scientists themselves have found the evidence. Researchers studying Venus's upper atmosphere have documented massive convection patterns, essentially hurricanes where cold and warm air masses collide. But if the temperature were truly uniform everywhere, there would be no temperature differential, no convection, no hurricanes. The convection itself proves a temperature gradient exists. The same research noted that atmospheric models show sulfur dioxide should be consumed by surface reactions within a geologically short time. It should disappear, and yet it persists. What if the answer is simple? What if Venus hasn't reached chemical equilibrium yet, because the event that created these conditions was recent? This is where the story gets extraordinary, because if Venus was recently bombarded, there should be historical records, and there are. Astronomers in the 17th, 18th, and 19th centuries had powerful telescopes trained on Venus constantly. It was the brightest object in the sky after the moon. In 1645, the Italian astronomer Francesco Fontana observed Venus and reported seeing an object orbiting the planet on a polar trajectory. He estimated its size at 1,500 to 2,000 kilometers. Venus, he noted, was emitting rays of light. His observation was dismissed as bad optics, but consider what Fontana actually described. A massive object moving across Venus, glowing red, while the planet emitted bursts of light. That's consistent with what a large asteroid impacting a planet would look like from 50 million kilometers away. 30 years later, in 1672 and again in 1686, Giovanni Cassini, one of the most celebrated astronomers in history, the man who discovered Saturn's ring division, observed the large object near Venus. He estimated it at 1/4 of Venus' diameter, roughly 3,000 kilometers across, orbiting at just 900,000 kilometers distance. That's inside the Roche limit, where tidal forces tear objects apart. The Roche limit is the distance within which a celestial body will be ripped apart by tidal forces. Any object orbiting inside it has days, maybe weeks, before it's destroyed and crashes into the planet. Cassini's object was deep inside this zone. Its fate was sealed. And Cassini wasn't alone. Over the next century, astronomer after astronomer reported the same thing. In 1740, British astronomer James Short reported a Venus satellite roughly 4,000 kilometers across and published his findings in the Philosophical Transactions of the Royal Society. In 1761, Jacques Montaigne tracked an object continuously for 8 days, making detailed sketches of a 2,000 to 3,000 kilometer body on a polar orbit. The orbital period was unstable, changing from 9 to 12 days. The orbit was decaying. Between 1645 and 1813, at least 30 observations of objects near Venus were recorded by a minimum of 12 professional astronomers. Each time the object appeared, was tracked for days or weeks and then vanished. Not drifted away, vanished. The standard explanation is that all of these experienced astronomers across 170 years, using different telescopes from different countries, all made the same mistake. Or these were asteroids captured by Venus's gravity, spiraling inward on unstable orbits and crashing into the surface one by one. The astronomers were watching Venus being bombarded, and each impact added more energy, more heat, more CO2, more sulfur to the growing inferno. The surface evidence backs this up, and it comes from NASA's own data. Magellan's radar mapping revealed grooves, long, deep tracks running pole to pole across Venus's surface. These tracks match the trajectory Fontana described, an object moving from pole to pole. They also match Montana's polar orbit observations. The scars on Venus align with what the astronomers drew centuries ago. Modern surveys have also found asteroids lurking near Venus's orbit. Asteroid 3002 VE68 follows a path between Mercury and Earth with Venus at its center. The larger 2020 AV2, over 2 kilometers across, orbits entirely inside Venus's path. These could be remnants of the same population that bombarded Venus S. So here's the question that ties it all together. If this bombardment happened recently, can we calculate when? If Venus's bombardment happened in the 17th to 19th centuries, just 200 to 400 years ago, then Venus should still be actively cooling, and that cooling rate should be calculable. It's just thermodynamics, Stefan Boltzmann law, radiative transfer through a dense atmosphere. Simulations show that from a starting temperature of nearly 2000 degrees, with Venus's current atmospheric density and an albedo of 0.88, the planet would cool to habitable temperatures in approximately 600 to 700 years. The math places the catastrophe roughly 100 to 200 years before the current thermal state, which lands squarely in the 17th to 18th centuries, exactly when astronomers were reporting objects near Venus. And there's a fascinating detail. Venus's current albedo is 0.88, meaning 88% of sunlight is reflected back into space. That's extraordinarily high compared to Earth's 0.30. Recent observations have detected increases in reflective material in Venus's upper atmosphere. The planet appears to be cooling faster than models predict. There's also a curious historical footnote. An 1871 issue of the Illustrated World Journal records a Colonel Drayton presenting to the Geological Society, using Venus as proof that a planet's distance from the Sun does not determine its climate. He stated that Venus was experiencing a period of extreme cold. Read that again. In 1871, a military officer told a room of scientists that Venus was freezing and used it as common knowledge. Just 150 years before our probes measured 470 degrees. Now the mainstream dating tells a different story. Scientists estimate Venus's surface was resurfaced 300 to 500 million years ago, based on crater counts and volcanic modeling. But that estimate assumes volcanism was the only mechanism. If bombardment was involved, the timeline changes completely. If the resurfacing was caused by asteroid bombardment instead of volcanism, you don't need millions of years. You need decades. The surface features, the coronae, the lava rivers, the craters, all of them are consistent with an impact event. Venus doesn't look like a planet that formed hellish. It looks like a planet that was made hellish. And now the question that should make this personal. If a swarm of asteroids could do this to Venus, what stops it from happening to Earth? Run the same simulation on Earth. Replace our atmosphere with 93 atmospheres of CO2. Raise the surface temperature to 2000 degrees. Heal all life. Melt the oceans into steam. Within centuries, Earth would look exactly like Venus does today. Same pressure, same temperature, same acid clouds. Venus is not an alien world. It's a preview. Now here's something worth noting about Venus's winds. At the upper troposphere, winds reach 100 to 140 meters per second hurricane force. But at the surface, Venera 9 measured wind speed at less than 1 meter per second. The lower atmosphere is so dense it doesn't have winds, it has currents, like an ocean. At the day-night boundary, cold and warm currents of semi-liquid CO2 collide, creating turbulent eddies, exactly like ocean currents meeting on Earth. This convection only happens when there's a significant temperature difference between regions. If the temperature were truly 470 degrees everywhere, this wouldn't exist. Let's pull back and look at the full picture, because when you lay out all the evidence together, a pattern emerges. 1. Venus's retrograde rotation can be produced by multiple sequential impacts, but not by any single known natural process. 2. Surface temperatures require a planet-wide heating event, not volcanism alone. 3. Atmospheric chemistry indicates a recent event, not billions of years of equilibrium. 4. over 30 documented observations of objects near Venus across 170 years. 5. The cooling rate calculation matches a catastrophe within the last few centuries. 6. An 1871 source describes Venus as cold. 7. NASA's Magellan radar data shows pole-to-pole surface scars matching historical observations. 8. Upcoming missions, DAVINCI with VERITAS and VISION, could finally provide the thermal and chemical data to test this hypothesis directly. If even half of this evidence holds, the implications are significant. Venus may not be a cautionary tale about slow atmospheric change. It may be a forensic case study, a planet transformed by cosmic bombardment within a time frame that overlaps with recorded human history. And that changes the stakes, because if this can happen to Venus, the only question that matters is what separates us from the same fate. The cooling models suggest Venus needs another 600 to 700 years to become habitable again, without any intervention. But with a modest increase in albedo, just a few percent more reflectivity, the cooling accelerates dramatically. The sulfur clouds already do most of this work naturally. Think about what Venus could become: a planet with Earth's gravity, Earth's size, a thick protective atmosphere, and eventually oceans, not of supercritical CO2 but of water, a second Earth right next door. All it needs is time. The standard story of Venus is simple: runaway greenhouse, billions of years, alien world. But the evidence tells a more complex story. A planet just like ours, caught in a cosmic bombardment, transformed not over geological time, but possibly within centuries. The evidence is in the radar maps, the atmospheric chemistry, the historical observation logs, and the math. NASA's DAVINCI mission will drop a probe through Venus's atmosphere in the 2030s, measuring composition at every altitude. ESA's Envision will map the surface in unprecedented detail. For the first time, we'll have the data to test this hypothesis rigorously. The answer to what turned Venus into hell may be just years away. Venus isn't just a warning about what the universe can do to a planet. It might be a promise that even after the worst catastrophe imaginable, a world can cool, stabilize, and one day become habitable again. If it happened to our twin, the question is,